My name is Marcel Böhme, and I look for PhD students at the MPI for Security and Privacy. My group works in software security, so we are trying to understand how to make software more secure and how secure software really is. My group is split into two parts. One part of the group develops tools that are very practical, and the other part of the group looks at the foundations of software security. In the part of the group that is very practical, we are trying to understand how we can find security flaws, so-called vulnerabilities, at the very large scale. And so in layman's terms, you would say, I'm trying to make machines attack other machines. And so why is this important? If you've worked in open source, you might know that the general idea is, with many eyes, all bugs are shallow. So what we are contributing with these tools is essentially a few more eyes that find bugs in software systems that could otherwise be exploited with malicious intent. In practice, some of my tools are used, for instance, at Google to find security flaws in more than 500 different open source software systems, including OpenSSL and many others that you might know, as well as the Chrome browser. In this practical part of my group, I'm looking at three different properties of automatic vulnerability discovery. One is called effectiveness, which is trying to find all the bugs, right? Maximize the number of bugs found. The second is called efficiency. We all have limited time, so maximize the number of bugs found within the limited time that we have. And if you're Google and you have 10,000 machines that you can run 24/7, then you would also be interested in a property called scalability. So how does bug finding scale across a number of machines? And so my group has made fundamental contributions to each of those in terms of understanding these properties and understanding the fundamental limitations of existing techniques. And this brings me to the second part of my group, which is looking at the foundations of software security. So what we are interested in is how secure are software systems, and specifically, given the tools that we have to find insecurity in software systems, what kind of assurances do these tools provide? So you might have heard about software verification, which allows to prove the absence of errors. We can prove the absence of security flaws in software systems. On the other hand, we have software testing, which does not prove anything. It just shows that bugs exist. And so it doesn't provide any guarantees. So maybe we can add guarantees to software testing, at least in a statistical sense. We understand software testing, which is just generating inputs for a software system, as a sampling process and make it amenable to statistics. And then can provide statistical guarantees about the absence of bugs. And at the same time, we have software verification, which is expected to provide formal guarantees about the security of a software system. But from a lot of recent work, we know that because of things like microarchitectural attacks and certain assumptions inbuilt in our formal proofs, that despite these formal guarantees, software systems are still vulnerable to attacks. So how can we quantify the assurances that even verification really provides about the security of these software systems? And so fundamentally, which kind of limitations do all existing techniques that we have ensure the security of or find vulnerabilities in software systems? What are the fundamental limitations? In order to understand that, my group is not only drawing from related topics, which are security, software engineering, and programming languages, but we're also drawing from more distant topics like biostatistics, probability theory, information theory, machine learning,